Welcome to the Explainer. If you're into organic chemistry, NMR spectroscopy is literally your ultimate structural map. But today, we're looking at what happens when our favorite, most reliable navigation tool, the simple N+1 rule, leads us straight into complete and utter chaos. And more importantly, I'm going to show you the exact visual tool that pulls us right back out. Let's get into it.
Here is our roadmap for today. We'll do a super quick recap of the basic N+1 rule, pinpoint exactly when and why it fails, and learn how to spot tricky diastereotopic systems. Then we'll bring in our hero, the tree diagram, to decode some seriously complex patterns together.
Section 1. The basic N+1 rule. Let's start with the comfort of our foundational status quo.
Okay, so the spin-spin splitting phenomenon is usually explained by the good old N+1 rule. You already know this one. Each type of proton basically senses the number of equivalent protons, that's our N, on the adjacent carbon atoms. Its resonance peak then splits into N+1 components. So 2 equivalent neighbors, you get a triplet. 3, you get a quartet. It works absolutely beautifully for simple linear molecules, as long as there is free rotation around those carbon-carbon bonds. That free rotation is key because it ensures the protons experience a perfectly averaged environment.
And just to ground us, the whole foundation of that rule comes down to atomic spin. A proton with a spin of 1/2 has exactly 2 allowed spin states when you put it in an applied magnetic field. It can spin clockwise, aligning with the field at a lower energy state of +1/2, or it goes counterclockwise, opposing the field at a higher energy state of -1/2. It's the interactions of these discrete neighboring spin states that give us those clean, symmetrical multiplets we totally expect from the N+1 rule.
Section 2. When the rule fails. Because, well, it's time to pull the rug out from under that perfectly averaged environment.
So as we just established, the N+1 rule fundamentally depends on free rotation. If you consider a molecule like 1,1,2-trichloroethane, the methylene protons are rotating freely. They share the exact same chemical shift, and they share the exact same coupling constant to the neighboring methene hydrogen. Everything is neat and tidy. But throw them into a biased conformation and that rotation is suddenly restricted. The protons are literally locked in place. They are no longer chemically equivalent, meaning they now have completely different chemical shifts and they couple differently to their neighbors.
When you actually look at the math behind this failure, the contrast is super clear. Under free rotation, the chemical shifts of proton A and proton B are equal, and their coupling constants to a neighbor, let's call it C, are also equal. Because of this, the geminal coupling between A and B essentially just zeroes out in the spectrum. You don't even see it. But in a biased conformation, the whole thing fractures. The chemical shifts of A and B are no longer equal. Their coupling to C isn't equal either. And suddenly, that geminal A-B coupling that was 0 before becomes a major factor that completely distorts the spectrum.
So, the million-dollar question here is, what exactly does our NMR spectrum look like when our protons are trapped in these rigid, completely different environments? Like, just how bad does the data actually get?
Section 3. Spotting diastereotopic systems. Let's see how this creates a totally new paradigm for our spectral analysis.
Well, the usual suspects for these trapped protons are diastereotopic systems. This happens when you've got 2 similar groups, like 2 hydrogens on a single methylene group, sitting on a carbon that is right next to a stereocenter. Because of that stereocenter's influence, those 2 protons are stuck in magnetically different environments. They are completely non-equivalent, meaning they'll have different chemical shifts, and get this, they will actually split each other.
To really see this in action, consider the proton spectrum for 4-methyl-2-pentanol. Honestly, at first glance, it looks like a chaotic forest of peaks. Because of the stereocenter at carbon 2, the methylene protons on carbon 3 are diastereotopic. Actually, it's wilder than that. Even the 2 methyl groups on carbon 4 are diastereotopic. So instead of getting those simple, predictable doublets or triplets, we end up with this massive, messy spread of really complex signals.
Zooming in on those diastereotopic methylene protons really shows us the depth of the problem. Instead of the N+1 rule giving us a neat little multiplet, each of these individual protons has a geminal coupling to its partner, plus 2 separate vicinal couplings to the neighboring carbons. The end result? Each proton shows up as a doublet of doublets of doublets. It is overlapping, it is incredibly messy, and the N+1 rule is completely useless to us here.
Section 4. The tree diagram solution. Now don't panic. To rescue us from this unreadable noise, we have a highly systematic graphical solution. We call it the tree diagram.
When protons are non-equivalent, we basically have to examine each hydrogen individually and track its coupling with every other hydrogen independently. It's a step-by-step process. First, you take the proton's initial signal and you split it using the largest coupling constant. Then, you take those new branches and split them again using the next largest coupling constant. You keep going down the line until you've accounted for all the couplings. Finally, you map the very bottom branches directly to the peaks on your spectrum.
Applying this logic to a molecule like styrene oxide reveals the true power of this diagram. The notoriously messy peaks are completely demystified by the organized geometry of the tree. For specific hydrogen, it's first split into a doublet by its trans neighbor. Then, each of those branches is split a second time by its cis neighbor. The result is a really clean doublet of doublets. By just dropping vertical lines down from the ends of our branches, the tree maps perfectly onto the real-world spectral data.
Section 5. Decoding complex patterns. So, now that we have our primary tool, how do we actively apply this to decode brand new complex data from scratch?
Let's think about a multiplet expansion from allyloxyanisole. Visually, it might look vaguely like a doublet of triplets, but chemically, we expect it to be split by 3 completely different single protons, which should technically make it a doublet of doublets of doublets. So, what is actually going on? Well, by measuring the distances between the peaks in Hertz, we can extract our exact coupling constants. We find one large vicinal coupling of about 5.2 Hertz and 2 smaller allylic couplings of 1.5 Hertz. And here is the kicker. Because those 2 smaller couplings happen to be nearly identical, the inner branches of our tree diagram actually overlap. The coincident branches add together, turning a complex pattern into something that deceptively resembles triplets.
To successfully pull this off in your own analysis, you definitely want to follow a few key rules. First up, always start with the absolute simplest pattern in your spectrum so you can extract your initial J values easily. Second, check for internal consistency. This is huge. If proton A splits proton B by 5 Hertz, then proton B absolutely must split proton A by exactly 5 Hertz. The coupling constants have to match perfectly across the molecule. And finally, once you've extracted most of your constants, use them to mathematically predict the tree diagram of the final, most complex pattern. If your prediction matches the visual spectrum, boom, your structural analysis is completely correct. By looking past the failure of simple rules and taking the time to map out these elegant tree diagrams, we realize something pretty profound. Those overlapping chaotic peaks, they aren't just noise. They are incredibly precise measurements of dihedral angles, restricted rotations, and locked conformations. So I'll leave you with this to ponder. How amazing is it that a flat, 2-dimensional line chart can secretly hold the exact 3-dimensional architectural secrets of the molecules that literally make up our universe? Keep exploring, and I'll catch you in the next explainer.